Okay. Thank you. Look at if you look at the bond. Okay. Originally, you have a bond between the proton and the hydroxide. Okay. Now you have a bond between the the OH, O, and the carbon. And so overall, if you look at the breaking bond, you broke a carbon oxygen pi bond because it's a double bond, one sigma bond, one pi bond. You broke a pi bond, okay? You broke this sigma bond, okay? So what two new bonds formed? One is OH sigma bond, one is a carbon oxygen sigma bond, right? So if you look at the based on what we establish in organic one, pi bond typically is a bit weaker than sigma bond. You're breaking a pi bond, a sigma bond, okay? You're forming two sigma bonds. So usually you'll consider this reaction as exothermic, if based on what we learn organic one, okay? But what's special here, the CO double bond is a kind of unusually strong double bond. So its pi bond is not that weak. So overall, this reaction is not necessarily exothermic. Okay. So whether the reaction exothermic or not depends on the stability of this carbonyl group. Okay. I hope you recall, the either last class or the class earlier, we discussed the stability of this and this. These are a pair of isomers. So you can directly compare the heat of combustion values. And the conclusion was this carbonyl, okay, is about 33 kilojoule per mole, okay, more stable than the aldehyde carbonyl. This is a crucial information, and you will gonna have a lot of implication in later reactions. The aldehyde carbonyl is about 33 kilojoule per mole. You don't have to memorize the number, but what you know is sizably more stable than the ketone carbonyl. Why aldehyde carbonyl is sizably more stable? Because the aldehyde group here only receive aldehyde carbonyl only receive stabilization from single alkyl group, and the ketone receive electron stabilization from two alkyl groups. Okay, so that makes ketone carbonyl group sizably, I'm not saying hugely, sizably more stable than aldehyde carbonyl. Okay, so if you extrapolate that, okay, you would say, okay, the carbonyl group in this one formaldehyde will be sizably less stable than this carbonyl. Sizably, maybe we don't have number to back it up because of these two are not isomers. Okay, so we can't measure heat of combustion. Okay, so but if we extrapolate that, this and this basically one alkyl group difference. Okay, in terms of stabilization, 33 kilojoule per mole. Let's just do roughly extrapolation. So this one another 33 kilojoule per mole less stable than this. Okay, so this kind of scheme you will see throughout the rest of the semester. Basically, the formaldehyde carbonyl group is substantially less stable than the regular aldehyde carbonyl, and regular aldehyde carbonyl is substantially less stable than the ketone carbonyl. Okay, and the less stability means they're going to be more reactive. Okay, and they also have greater tendency to react. So what kind of reaction is typical for carbonyl groups? Basically, carbonyl group is highly electrophilic. A typical reaction is nucleophile attack carbonyl carbon. Okay, so you can say out of all those carbonyl, this one is most electrophilic. This one is second. This one is third. Okay, so this give you clear explanation why if you look at equilibrium constant. Okay, the formaldehyde is actually hydration equilibrium constant. Formaldehyde is really high, 2000. Okay, so that makes the formaldehyde hydration is heavily favor the hydrate side. And aldehyde, the regular aldehyde, the equilibrium is kind of highly reversible. Two sides are very similar. Equilibrium constant is 1, right? And then ketone, the equilibrium doesn't really favor the side of hydration, favor the ketone, just carbonyl group itself, because this carbonyl is most stable, best stabilized, least electrophilic, and this carbonyl is least stable out of the one we show here, most electrophilic. Okay, and the question about those effect. So electronic effect is a major effect, impact hydration equilibrium, major effect. Okay, and steric we're going to talk about here plays a minor effect. Okay? So now here we're only talking about those carbonyl compounds only with regular alkyl group attached to the carbonyl carbon, as we learned as early as like chapter 5 organic 1. We know when we have alkyl group attached sp2 hybridized carbon, alkyl group stabilize sp2 hybridized carbon by releasing electron to it. Okay? Releasing electron to it. Okay? So if we replace substitutes on the carbonyl carbon with not the electron releasing group but electron withdrawing group, what do you expect? If electron releasing group makes carbonyl more, less electrophilic, make it more stable. Okay. alkyl groups are electron releasing groups. Okay. Have an electron releasing group, release electron carbonyl, make carbonyl more stable, less electrophilic. So if you place electron withdrawing group on carbonyl carbon, then what happens? Will make it more electrophilic, so more like undergo hydration. Okay, so that's what exactly we observe here. If we replace, the alkyl group with a higher electron withdrawing group, as we learned in chapter 13, trifluoromethyl group. Remember, that's a typical electron withdrawing group. We learned in chapter 13, it reduce electron density away from aromatic ring. So it does the same thing for the carbonyl carbon. So this guy, if you have two of them attached to carbonyl carbon, the hydration equilibrium constant is actually 10 times greater than formaldehyde, because this trifluoromethyl group not only does not supply electron to the carbonyl, it actually takes it away to make it less stable, more willing to react. And any other questions about electronic effect? Yes.
The more stable it is, the less
if more stable the carbonyl group is, there will be less tendency to undergo hydration, because it's more stable, they are happy for what it is. Okay? So the more stable it is, you see lower hydration equilibrium constant. So go from here to here. Okay, carbonyl become more and more stable. So the hydration equilibrium constant becomes smaller and smaller. And once the carbonyl group become more stable, reaction rate also decreases. Okay, because that's usually the case, although that's not absolute always the case. You can understand this. Okay, if this is a carbonyl compound. Okay, if this is a say hydrate. Okay, so if the carbonyl compound, assume the activation energy doesn't change much. If you make the carbonyl compound less stable, you increase its potential energy, then the activation energy becomes smaller. Okay, so it typically reacts faster. Okay, yes.
So the more stable it is, the less likely it's going to undergo a hydration.
Yes, that's absolutely true, because of when this one is more stable. Okay, let's say it come if let's say look at these three things. Okay, three carbonyl groups, green, black, blue. If you look up, if the position represents the potential energy, the blue one most stable, and the green one the least stable. And then the hydrate, we assume that the stability doesn't affect, it doesn't change too much. Okay? Once the carbonyl group become less stable, then you see the this overall reaction become more exothermic. Okay, if the overall reaction become more exothermic, the equilibrium constant become greater. Okay? And if it become less, if the carbonyl could become more stable, then if you look at overall reaction, the potential energy change from here. Okay, let's say from green to blue. Green to blue, this reaction is exothermic reaction. Okay, but if you from the blue to the black one, say if you from green, this is a hydrate. Okay? This is a hydrated potential energy. Hydrate. Okay, the hydration product. Okay, so if green go to hydrate, that reacts exothermic. Okay, but if you move to blue to hydrate, become endothermic. So that's what happens from formaldehyde to ketone. Okay? If regular aldehyde, you see the potential energy kind of similar. Okay, that's you see the equilibrium constant close to 1. Any other questions? So basically this is a major effect, is electronic effect, depends on how well the carbonyl group is stabilized. If the carbonyl group is better stabilized, less willing to undergo reaction, also react slower. Okay? The steric effect plays a minor role, but doesn't mean it doesn't play any role. Okay, so if you look at the magnitude of steric effect, you can compare these two guys. Okay, see you go from the least steric hindering LQ group is methyl group to one of most steric hindering, biggest, bulkiest LQ group is tertiary butyl group. You see, go from here to here, the equilibrium constant changes by 5 times only. Okay, but from here to here, a change of 1 carbon, you reduce the equilibrium constant by 2,000 times. Okay, this here is the electronic effect change. Here is steric effect change. So steric effect is a minor effect, but the steric effect, a bigger, larger, bulkier LQ group will make it less favorable to form hydrate. And this is understandable because if you look at in the hydrate, the carbon is sp3 hybridized. Okay, sp3 hybridized. So the bond angle become 110. Okay, 110 degree. So if you have bigger group, they will be more likely to feel the steric effect from neighboring group, right? Because from 120 in the carbonyl side, okay, this is 120 degree. Here is 110 degrees. Okay, so the space between two adjacent group becomes smaller in the hydrate. So if you have a bigger the substituents, you will make it the hydrate formation less favorable because of 110 in the hydrate and 120 in the carbonyl compounds. Okay, so that's why you see if you have a large substituents, you will see hydrate become less likely to happen. But it is a minor effect. Okay, not the major effect. Any other questions? Now the hydrate, the hydration process is a relatively fast process. So if we look at the mechanism in a neutral hydrate, that's using acetone as an example. If you look at a mixture of water and acetone, the electrophile, no question, is the carbonyl is acetone. The carbonyl carbon is electrophilic adder. I hope you 100% clear now. If you have a carbonyl group, usually carbonyl carbon is electrophilic adder because that's the most positive charge adder, usually. Okay. Now, what is the major nucleophile in the mixture of acetone and water? If it's neutral, what is the major nucleophile? Just water or acetone. Acetone itself can be nucleophile because carbonyl oxide is nucleophilic. Okay. But let's say we're talking about hydration, so water will be major nucleophile. Not hydroxide ion, not hydronium ion, because with the pH, let's say neutral one. So the hydroxide ion concentration will be extremely low. Okay. So then the rate limiting step will be, okay, this one attacks here. That is the rate limiting step, okay. So this rate limit step, the rate depends on what? Obviously, you know, the concentration. Let's take out the relationship of concentration. So let's say the overall rate R equal to K times the carbonyl concentration and the water concentration, right? That's what the, you know, the rate says, okay? And obviously this, you know, the equilibrium constant, okay, characterize how fast this reaction is. And but how fast this K depends on what? Depends on the electrophilicity of the electrophile and the nucleophilicity of nucleophile, right? And the, you know, the problem is, although this reaction is still relatively fast, okay, water, okay, nucleophilicity, if you recall what we learned in chapter 6, organic 1, water is not a great nucleophile. Water is typically classified as a weak nucleophile. Okay? If you check that the nucleophilicity table, it's assigned as nucleophilicity of 1, okay, is a weak nucleophile. Okay, so the this reaction is still reasonably fast. Okay, but if you add either hydroxide ion, okay, or proton acid into this hydration system, the hydration rate will be substantially faster. Okay, so basically either you're adding base or adding acid can catalyze the hydration process. So why, you know, the adding, you know, acid, either acid or base can catalyze the process. Let's first look at the, you know, the mechanism of base catalyzed hydration. We say base catalyzed hydration means, okay, we're adding to base into a hydration system, water, mixture of water and the carbonyl, or you know, water or the ketone or water aldehyde. The reaction will be substantially faster, usually at least 100 times faster. Okay. So what is the mechanism? Adding, you know, base in the system can make the reaction faster. Okay. So the biggest reason the base can accelerate, you know, the hydration is because if you're adding base into water, what form? Okay? If you're adding base into water, typically you form hydroxide ion, right? Adding to water. Okay. So the hydroxide ion is the conjugated base of water. So the both hydroxide ion and the water can serve as nucleophile. The major difference is, you know, even the attacking atom is the same. Oxygen is attacking nucleophilic attacking atom. So what's the biggest difference? Biggest difference is in water, the oxygen carries partial negative charge. Okay, maybe 0.4, 0.5, 0.6. I don't remember exact, but you depend on the computation way you do it. 0 point something unit negative charge. And how about the hydroxide ion? The hydroxide ion, its whole unit of negative charge. Okay, so the what, you know, because of you have much greater negative charge on hydroxide on the oxygen atom in hydroxide ion compared to amount of negative charge in water. So that makes hydroxide ion a lot more nucleophilic than water. And again, if you check that nucleophilicity table in chapter 6, you will find on average hydroxide ion about 10,000 times more nucleophilic than water. Okay, so this you know, this difference between the pair of nucleophiles that are conjugate to each other, this relationship usually holds true. Let's say if you look, for instance, if you look at this pair of nucleophile, they are also conjugated to each other. The top is conjugated base, bottom is conjugated acid. Their nucleophilicity also the top one, the bottom 10 to the 4th to the 10 to the 5th more nucleophilic than bottom. Okay? Just because of nucleophilicity, after all, ability to give out lone pairs. Okay? So if you have a greater negative charge, you'll make it a lot likely to give out negative charge. Okay? So the key reason is the hydroxide ion is a lot more nucleophilic than water. Okay? So if you have a sizable concentration of hydroxide ion in water, hydroxide ion being about 10,000 times more nucleophilic than water, you will attack carbonyl carbon far faster than water does. Okay? So if you add a base in the system, this is a rate limiting step. Okay? But this rate limiting step, if you compare with this rate limiting step, okay, this rate limiting step is significantly faster, okay, because hydroxide ion is about 10,000 times more nucleophilic than water. Okay? So as long as there's a sizable concentration of hydroxide ion in the solution, hydroxide ion will be the nucleophile to attack the carbonyl compound simply because of its more nucleophilic. Greater nucleophilicity makes the reaction faster. And this attack gives you alkoxide ion. Okay? And then the next step, alkoxide ion will, get a proton from water and then regenerate hydroxide ion to do, next step nucleophilic attack. And you see the hydroxide ion is not consumed in the reaction because consumed first step, then regenerating second step. So yes, hydroxide is a catalyst. Okay? So the key reason why base can catalyze hydration because of you have if you add a base in water, it can generate hydroxide ion, and hydroxide ion is 4 orders of magnitude more nucleophilic than water. So they can attack the carbonyl carbon faster a lot than water does. Okay. Now, what about adding acid? Why adding into the hydration reaction also can speed up the hydration process. Okay? And this is because of totally different reason. Okay? If you add acid in water, obviously you're gonna have hydronium ion. Okay. Do you think hydronium ion is more nucleophilic than water? No way, because even not nucleophilic, because hydronium ion is a positive charge. Okay. How could further give a lone pair? So no way nucleophilicity will be better. Okay. But keep in mind such a nucleophilic attack reaction rate, okay, depends on both the reactivity, the electrophilicity of the electrophile, and the nucleophilicity of the nucleophile. If either one becomes faster, say in the case of base catalyzed hydration, we say because we are having a more nucleophilic nucleophile, the reaction is faster. Electrophile didn't change, right? But if you in acid catalyzed process, we know we're not going to have a better nucleophile because the hydronium ion is not nucleophilic, and you won't have hydroxide ion because in acidic environment, the hydroxide ion concentration is close to nothing. Okay? So then only thing could make a reaction faster is somehow maybe if you don't have more powerful nucleophile, so what can make a reaction faster? It's nucleophilic reaction. If you cannot have a more powerful nucleophile, then how can you make a reaction faster? Yes, you have better electrophile. Okay, so that's what happens. Okay, so in the acid catalyzed reaction, you have hydronium ion. Okay, the hydronium ion, which is a proton donor, can donate a proton to the carbonyl oxygen. We know carbonyl oxygen is nucleophilic, right? Carbonyl carbon is electrophile, but oxygen is nucleophilic. So this basically can transfer proton to the basically you can make the carbonyl oxygen is a nucleophile, and the base take a proton from hydronium ion, give you a protonated carbonyl group. Under this proton carbonyl group, under the, I just, the such you probably can write this one, okay, into its other resonance form. See, this the bottom resonance form, although it's not as stable as the top one, but can clearly show you this, the protonated carbonyl group, okay, has a carbocation character, okay, and compared to the carbonyl group before the protonation. Before the protonation, you also can write this polar resonance form. Okay. Now you see a difference here. The before and after protonation. Before the protonation, you have a negative charge oxygen connect to the carbocation. If you view carbonyl as a carbocation, but after protonation, now you have a neutral group attached to the positive charge carbon. So if you compare the bottom two chemical species, which one will be more electrophilic? Left side one or right side one? Obviously right side one, okay? So because the protonation makes the carbonyl carbon substantially more electrophilic than before, okay? So if the carbonyl carbon become more electrophilic, so even a pool nucleophile like water, neutral water, can attack this carbonyl substantially faster than this attack, okay? Substantially faster, maybe about 1,000 times faster. Okay, so and in the acid catalyzed hydration, the second this step is a rate limiting step. Okay, slow step. Okay, first step is just faster. The acid Bronsted acid base reaction, and obviously this guy can lose a proton to water. Okay, the addition product can lose a proton to water. Okay, water can take a proton away from this one to regenerate the hydronium ion. Okay, to show that the hydronium ion indeed is a catalyst. It participates in the reaction at the beginning of reaction, but regenerate at the end of reaction. So hydronium ion is a catalyst. Okay, so the difference between base catalyzed hydration and acid catalyzed hydration is that base catalyzed hydration makes reaction faster by providing a more powerful nucleus. And in acid catalyzed hydration, by protonating the carbonyl oxygen, okay, we are generating a more powerful electrophile. Okay? And the protonation of carbonyl will generate a more powerful electrophile, and you will see many times in the the later part of the topics. Okay, you will see many times. Just protonation of a carbonyl will generate more electrophilic carbonyl. So they will accelerate subsequent nucleophilic attack. Any questions for the acid catalyzed hydration? So whether you can have acid or base catalyzed hydration depend on your reaction condition. Basically, whether the pH is substantially below 7 or substantially higher than 7. Okay, you're gonna have either acid or base catalyzed, the process. And here I also provide a spectroscopic evidence of the protonation of carbonyl group does make the carbonyl carbon more electrophilic. And we know that the chemical shift of carbon-13 chemical shift reflects electron density on the carbon. Okay? So in a neutral acetone, the carbonyl carbon has a chemical shift of 207 ppm, very large chemical shift value. So we know that is the reason why we can confidently say carbonyl carbon has very low electron density only. So it's electrophilic. Okay. So what happens if you protonate it? The chemical shift further increase to a crazily high value, 251. Okay, why such a crazily high chemical shift value? Because protonation makes original electron deficient carbonyl carbon, even more electron deficient than before. Okay, and the question about hydration. So those two catalyze the hydration process does not impact the equilibrium itself, only impact the rate. Okay? And but these two mechanisms, based on acid catalyzed mechanism, you will see many times later on. Okay? So be sure to pinpoint the most important factor in the acceleration mechanism. So in a base catalyzed acceleration mechanism, because you are getting a much more powerful nuclear. Okay? In the acid catalyzed mechanism, you are getting much more powerful electron. So this is so here basically we conclude the hydration. We have quite a few other the nucleophilic. So this hydration process is a nucleophilic addition to the carbonyl carbon. So in all those in the hydration process, we always involve a nucleophilic attack to carbonyl carbon. Okay. And that's why we call and the overall product is addition to the carbonyl group. So we call the nucleophilic addition to carbonyl group. And the nucleophilic addition to carbonyl group is a characteristic reaction of ketones and aldehydes. And we will learn quite a few other nucleophilic additions. So next one we will see is called cyanohydrin formation. Cyanohydrin is a product where you have a carbon simultaneously bound to the OH group. This is how the name hydrogen comes from. Okay, and also this same carbon also bound to the CN group, cyano group. So that's why I call cyanohydrin. Okay? And the cyanohydrin is formed by nucleophilic addition of hydrogen cyanide to the carbonyl group. And this reaction is a reversible reaction, just like hydration. So you can view this reaction, analyze this reaction in a similar manner as the hydration process. So if in a hydration process we have this, okay, and then and then we have the O and I think it's too far. And that's the hydration, okay. And you can consider hydrogen cyanide, okay, consists of proton and a cyanide ion. So as far as the reaction goes, it's pretty much it can be viewed as very similar as hydration. So the proton goes to carbonyl oxygen, the nucleophilic cyanide goes to carbonyl carbon. Okay? That is pretty much the same. Okay? And the hydrogen cyanide is very rarely used for a number of reasons. First, hydrogen cyanide is a gas, extremely toxic, okay? So the very dangerous to use. Second, if directly using hydrogen cyanide solution, okay, the reaction will be slow for the reason we're gonna see later on. Okay, and in real world, we almost always using alkaline cyanide salt. So either potassium cyanide or sodium cyanide. Okay, they are equivalent. Okay, these two things still very toxic, but at least they are solid. So you will not accidentally inhale it. Okay, so in real world, we always using potassium or sodium cyanide react with ketone aldehyde, then followed by the hydronium ion adding acid. sulfuric acid into the system. Okay. So the mechanistically, if you do this kind of reaction, basically you will see, let me see, like here, okay? If you have sodium or potassium cyanide, you can consider the equivalent is a cyanide ion, the supplier. So you can forget about the sodium or potassium cation, they are spectator ions. And the cyanide ion, I hope, okay, you recall from again that nucleophilicity table in chapter 6. Cyanide ion is a very good nucleophile. It's equivalent to hydroxide ion when it comes to nucleophilicity. And the carbon is nucleophilic atom. So obviously the cyanide ion will attack the carbonyl carbon very rapidly, okay, and give you corresponding alkoxide, and that is the rate limiting step. Okay? This step is pretty much the same as OH minus hydroxide ion attack the carbonyl, pretty much the same. Why we using sodium potassium cyanide? Because of the sodium potassium cyanide can provide a high concentration of cyanide ion. Okay, and if you have higher concentration of nucleophiles, then the reaction will be really fast. So that's why we always use sodium potassium cyanide. Okay, react with ketone carbonyl first. Okay, and we will get this one. Okay, then if we want to get the cyanohydrin, we can just after the reaction finishes, okay, we add the hydronium ion. Okay, we get the cyanohydrin product. Okay, that's the real reaction. Okay. So that is a real reaction. So you have the aldehyde. This part, no matter how complicated it is, it's unless this this is a aromatic halide, usually aromatic halide, unless they have nitro group attached to it, usually they don't really want to undergo nucleophilic reaction. So you don't need to worry about this part. Okay, it just will be carried over in the product. So what happens is cyanide ion attack carbonyl carbon. Then in second step, you add sulfuric acid, you get cyanohydrin. Okay, you get nearly 100% yield. So the reaction cyanide attack, carbonyl is kind of the same as the base catalyzed hydration. Okay, so the other way you can do this reaction is you also can take the ketone aldehyde, okay, then using sodium cyanide, okay, and you're using a mixture of sodium cyanide or potassium cyanide with hydrogen cyanide. This also going to be fine. And here the sodium cyanide could serve as a catalyst. Okay, basically with the cyanide ion, okay, attack here. This is a rate limiting step. Give you its corresponding, the alkoxide. Okay. Then the hydrogen cyanide, okay, can serve as the acid. Okay. Give you the cyanohydrin product. And regenerate the cyanide ion. Then you see, okay, cyanide ion indeed is a catalyst. The participating reaction before that regenerate at the end of the reaction. So this is the role of cyanide ion here is exactly the same the hydroxide ion played in the basic catalyzed hydration. Okay? And the direct reaction of hydrogen cyanide react with carbonyl is really slow. Why? Because of hydrogen cyanide is a weak acid. The pKa is around 9.1. Okay, so if you're just using hydrogen cyanide, itself, it will not be able to generate a sufficient amount of cyanide ion to let the reaction go really fast. Okay. So we know that if you're adding the cyanide ion into it, it can catalyze the reaction just like a base catalyzed hydration. Okay. Now we also learn that in hydration process, adding base can make the reaction faster. We also can add acid and make the reaction faster. So can we add acid, okay, to catalyze, the cyanohydrin formation, from hydrogen cyanide to the carbonyl group? Yes, I see somebody nodding head. Okay, but the why acid catalyzed hydration, okay, can help is because two reasons. Okay, one is you have acid catalyzed. When you have acid, okay, the acid can protonate the carbonyl carbon, okay, and this protonation give you a more powerful electrifier, okay. So this is a more electrophilic, okay, more electrophilic than before, okay. But this approach only will work, okay, if your neutral nucleophile can do the nucleophilic attack, okay. Here, water, okay, neutral nucleophile indeed can do the nucleophilic attack, but if you do let's say, if you do this reaction, okay, HCN, sulfuric acid, okay. So if you do this reaction, yes, you will have this one, no question, okay. You will have this, okay. But the problem is, can you have this hydrogen cyanide serve as a neutral nucleophile to attack this carbonyl? Yes or no? Hydrogen cyanide, okay, in theory, it can serve as a nucleophile, okay, but only nitrogen can attack, okay. If nitrogen attack, is it still the cyanohydrin? No. So this one won't work because neutral hydrogen cyanide, okay, cannot serve as a nucleophile with carbon as a nucleophile. So it won't work. Okay. So this is doesn't work because of if you in acidic environment, the hydrogen cyanide, okay, will not work as a nucleophile, okay, with carbon serving as a nucleophilic attacking element because carbon, it has all the fully bonded, no lone pair to provide. Okay. So this the acid protonation really doesn't work here. Okay, but the base base catalyzed reaction or cyanide catalyzed reaction work here. Okay. Now, if you look at the equilibrium constant of cyanohydrin formation, the trend, okay, is exactly the same as the hydration. You see the formaldehyde has a greater equilibrium constant than regular aldehyde, okay? The regular aldehyde has a greater equilibrium constant than the ketones, okay? Now those two both are regular aldehydes, okay? So can anyone provide a reasonable explanation why this aldehyde has about 100 times lower equilibrium constant than this aldehyde? Both are aldehydes, okay? Yes?
Because the benzene ring draws out more electron density.
Draws up more electron density, right?
Away from the carbon, from the carbonyl.
So if benzene ring draws electron density away from carbonyl, you think it make it more likely to react or less likely to react?
More likely to react.
Yeah, if more likely to react, it should demonstrate a higher equilibrium constant than the regular aldehyde, right? Yes, Julia. That is true, but if you think about the let's say if you donate by what mechanism? Electron donation have two mechanisms. Okay, inductive effect, okay, or resonance effect. Yes, resonance effect. That's the major one. Both are you right? Okay. Obviously, the fact that this one has a less equilibrium constant than regular aldehyde means the carbonyl carbon in the benzaldehyde, okay, this guy, okay, must have a less higher electron density than this one, okay. But why it becomes resonance, okay? Because we have a pi electron delocalization here, okay. So that makes the carbonyl carbon receive a bit more electron from the aromatic ring because of pi conjugation. And you also notice from the chapter, I want you put connect all the knowledge together. In chapter 13, yes, 13, I believe so. The electrophilic aromatic substance, chapter 13, right? Once you have a carbonyl carbon bound to the ring, it is what kind of group is considered? What comes to electrophilic aromatic substitution? It's deactivating group. It's reasonably powerful. We not say super powerful, but reasonably powerful deactivating group. Means the ring indeed give electron density to the carbonyl group. Okay? And mostly because of the the resonance effect. So basically you can see all makes sense what you learned in chapter 13 and what you learned here. Okay, so that's hydrogen cyanide. Okay, so the trend is still the same. So when you look at equilibrium constant, the more stable the carbonyl it is, the less willing to react. Ketone has the most stable carbonyl, so that has the smallest equilibrium constant. And this aldehyde carbonyl is a bit more stable than this because of additional pi electron delocalization. So it's 100 times less likely to undergo cyanohydrogen formation than regular aldehyde. Okay? Regular aldehyde is about like 20, 30 times less likely to undergo cyanohydrogen formation than the aldehyde. Okay? Formaldehyde. Because of formaldehyde carbonyl, among all the carbonyl here, is the least stable one. Okay? So obviously, if I place another one, this one, okay, if I ask you what will be its cyanohydrogen formation equilibrium constant, should be where you should place it. If you have this aldehyde, where should you place it? Should be to the even left of formaldehyde, okay? Because of that CF3 is a very powerful electron withdrawing group. It activates the carbonyl group instead of deactivating. I don't know the number, but should be higher than formaldehyde. Any question about cyanohydrogen formation? If not, let's look at the next one. Next addition reaction is the alcohol. Okay, nucleophilic added to the the aldehyde or ketone. Okay, so the alcohol you can look at is pretty much the same way as not same way, similar. You can dissect alcohol in a similar way as water. Huh? So if you look at water, we can say, okay, water consists of proton and hydroxide ion. Okay, that's typically we view water, right? Proton and hydroxide ion, and then if you have alcohol, you have you can view as a proton and alkoxide ion. Okay. Indeed, if you have alcohol, it can ionize, form proton and alkoxide ion. Okay. So this can directly compare alcohol with water. So if you have alcohol nucleophilically add to the carbonyl group, now obviously which part can add to the carbonyl carbon, which part can add carbonyl oxygen? So the which part can add carbonyl carbon? The electrophilic, the proton, add carbonyl carbon. Okay, and the nucleophilic alkoxide will be add to the carbonyl oxygen. Okay, so that's what you could expect without the any additional knowledge you will be learning in this section. So if you have a carbonyl group, okay, if you react with alcohol, certainly you're gonna expect those are the atoms originally from the carbonyl, the carbonyl compound, okay, and then the nucleophilic part, OR, okay, can add to the carbonyl carbon, and the electrophilic part, the proton, add to carbonyl oxygen. So that's what you expect. Okay. So indeed, that's what you will be getting if you just let alcohol react with a ketone or aldehyde in neutral or basic environment. The reaction will stop here. Okay. Will stop here. If you let the alcohol react with neutral environment. Okay. But and this compound, okay, is addition product between alcohol and the ketone and aldehyde. If assume, let's say, for the sake of simplicity, let's say we assume we're just talking about aldehyde. Okay, if you have aldehyde, and if you add a molecule of alcohol to aldehyde, we call hemiacetal. Okay, and that's the product we'll be getting if such addition happens either neutral or basic environment. Okay, but if this reaction happens in an acid catalyzed environment, the reaction won't stop there. Okay, you will proceed. Okay, to next step. Okay? And become this called acetal. Okay, and the first step is a nucleophilic addition, just like in the same way as the hydration or cyanohydrin formation, because we added alcohol across the carbonyl group, right? But in the second step is actually is a nucleophilic substitution. Why? We are replacing this OH group by the OR group. Okay. So the rest of no change will replace OH by OR. Okay. And the forming of water is a nucleophilic substitution. Okay? So this two stage. First stage is addition. Second stage is nucleophilic substitution. Okay? So and the similar reaction could happen to ketones. Okay. So if this reaction, two-stage reaction, they happen to the aldehyde. Okay. So in the first stage product is addition product, we call it hemiacetal, and the second stage product we call the acetal. Okay. So if you look at this compound, okay, is technically is ether, okay, because of you see in both oxygen atom, two sides connect to alkyl group. So technically it's ether, okay, and this one is both an ether and an alcohol, okay, but this one just an ether, okay. So but anyway, I don't really ask you to memorize them, just I guess, but give you some historical account about this just for historical reason called acetal. Okay, and this one because in the middle way is called hemiacetal. Okay, and the similar reaction can happen to ketones. Okay, and if a ketone react with you know the alcohol with 2 mole equivalent of alcohol in acidic environment, and that product called ketones. Okay, and both ketones and acetals, they are ethers. So the acetal formation is often thermodynamically favorable. Okay, means that you know from here to here in acidic environment, usually you're gonna see a good conversion. Okay, at equilibrium. Okay, but the keto formation usually is not. Okay, with you know it's kind of understandable. Okay, why keto formation is less favorable, and for 2 reasons. The biggest reason is you know the ketone carbonyl is about 33 kilojoule per mole less stable than, oh no, sorry, ketone carbonyl is about 33 kilojoule per mole more stable than the aldehyde carbonyl. 33 kilojoule per mole is a pretty large stability difference. Ketones about 33 kilojoule more stable than aldehyde carbonyl. That means it will be 33 kilojoule per mole less willing to become the product. Okay? And even for aldehyde, from here to here, the you know the enthalpic, you know the driving force is not that large. It's you know somewhat favorable. For ketones, such a reaction becomes less favorable. Okay? So let's say if for aldehydes, okay, assume this reaction is 20 kilojoule per mole exothermic. Okay, right? Now for ketones, will be 13 kilojoule per mole endothermic, because ketones is about 33 kilojoule per mole more stable than aldehyde. So if aldehyde is like 15, 20 kilojoule per mole exothermic, favorable, right? And ketones would be like 13 or 20 kilojoule per mole endothermic, not favorable. Okay, so kind of that's a major reason, okay? Because of ketone carbonyl is about 33 kilojoule per mole more stable than aldehyde. But stereohydrins also plays a role here because of ketones. If you look at ketone, just compare to you know the acetals. Look at 2 acetal structure. Okay, one is the aldehyde, right? If this aldehyde, let's say, react with ethanol, say we add a sulfuric acid, okay, then it eventually become so this is acetal formed from aldehyde, okay, and if it's a similar reaction but on a ketone, so if you look at for ketones, in the acetal, the keto side, okay, this is called keto. This is called acetal. This is acetal, okay. This is keto, okay. So the keto, you're gonna have if you look at this, the stereohydrins, okay, around the central carbon, okay, is sizably larger than the steric hydrins in the acetal, because of you see the central carbon sp3 hybridized, okay, and in the keto you're gonna have you know the additional methyl group replace hydrogen. You're gonna lead to substantially larger stereohydrins, but this is a minor effect. Okay? The major effect is still this carbonyl is about 33 kilojoule per mole than this carbonyl, more stable. Okay, this carbonyl is 33 kilojoule per mole more stable than this carbonyl. Okay, more stable, less willing to react. Okay, so the ketones usually doesn't want to react, but except if you have 5 or 6 membered cyclic keto, can be prepared from the ketones, then the reaction could be somewhat thermodynamically favored because the formation of a really stable rings. So how do you form a cyclic keto or acetal? So instead of using a regular alcohol, we can using a diol. Like here, it's we are using ethylene glycol diol. Okay, we can form a 5-membered ring. The 5-membered ring include the 2 carbons in the diol and the 2 oxygen in the diol and the carbonyl carbon. This gives you 5-membered ring. And if you recall what you learned in organic 1, 5 and 6-membered ring, they are most stable rings. Okay? So their formation are generally pretty favorable. So in this particular case, the reaction can proceed to the reasonable conversion at equilibrium. And here, the additional measure was applied to shift the equilibrium to the right side. Okay, that's the purpose of adding benzene. Okay, so why we add benzene here? Anyone recall? We talk about in chapter 16. Forgot about it. Okay, not exactly. Anyone recall what's the goal of benzene here? First, do you think benzene is representing reaction? No, it doesn't really reaction at all. Okay. So what's the goal adding benzene here? It's not really solvent, or neither serve as solvent, because this reaction, all these reactions are ionic based reaction. Benzene will not be a good solvent. Okay? Benzene is a non-polar solvent, so will not promote ionic reaction. But benzene is added here to shift the equilibrium to the right side. But how can benzene shift the equilibrium to the right side? We talked about chapter 16. Anyone recall? Yes.
The molecule which dissolves using for it's like a cyclic something.
Not exactly. Anyone recall chapter 16? We talked about yes.
Is it going to be the same thing that was in chapter 16 where the passage of these inhaled by this is moving with the stomach acid?
Oh, you are talking about the ground ether?
Yeah.
No, it's not. Anyone? Chapter 16. Fischer acidification reaction. Anyone recall that about morphine? So this reaction, although somewhat favorable, okay, but it's still considered, equilibrium. Okay? So it forms water, right? So if you can have a way to continue to remove water from reaction system, then by the Chaliad's principle, the equilibrium can shift nearly completely to the right side. Okay? So benzene can form azeotropic mixture with water. So you can continually bring water out of the reaction system. And you remember, I don't know whether you guys remember, but we talked about, I forgot the name. But anyway, that's somebody's name. Anyway, this is called the process called azeotropic distillation. So the basically benzene can boil at a temperature, blending in the water and boil together at a temperature below the boiling point of both components. So that can help bring water up. And then the best part is because benzene is lighter than water. Okay? When the liquid comes out the side arm, then benzene can flow back to the flask, continue bring the system, bring water out of the the reaction mixture. So help shift equilibrium to the right side. And P toluene sulfonic acid. What's the goal here? Yeah, this thing called Dieng-Stark distillation adapter. Okay, so the benzene gonna boil together with the water coming out of the the condenser being condensed into here. Then benzene and the water gonna phase separate. Water lower, okay, benzene in the top. The benzene can flow back to the flask, bring more water out. Okay, so that's how why we add a benzene there. Okay, and the P toluene sulfonic acid. Why are we using this acid? What's the goal of P toluene sulfonic acid? Huh? Yes, that's kind of. But why we put toluene sulfonic acid? Because you have you can just simple as sulfuric acid, also might have different some organic stuff. Yeah. So you have the benzene ring connected sulfonic acid with more soluble organic solvent. So this basically organic version of sulfonic acid. So this standard procedure to convert a ketone or aldehyde carbonyl into its acetal or ketone. And this procedure you will see quite a few times in this chapter. Then look at the mechanism. Okay, so I'm not going to talk about the mechanism of the first stage. Okay, the first stage mechanism, please go home, draw by yourself. It's exactly the same way, three-step mechanism as acid catalyzed hydration. Exactly same. Okay, exact same. So basically first the protonation of carbonyl make activated carbonyl. That's a faster process. Second, the neutral alcohol attacks activated carbonyl. Then third step, the addition product, the loser proton, they give you this neutral, the hemiacetal. Okay. Now we're gonna look at what happened in the second stage reaction mechanistically. Okay. And this is actually a nucleophilic substitution reaction. Okay. So if you look at second stage, so the second stage we have acid there. So one of those two oxygen atoms will be protonated. Okay. So technically both oxygen atoms could be protonated, but if you go home to draw the mechanism of first stage, you will see that if you protonate the bottom oxygen, red one, okay, the reaction will basically trigger going back to the starting material. So it's not productive. So we don't need to consider that. Okay. So we can look at all the top oxygen can be protonated. Okay. And this is a faster biomolecular process because of it's involved strong acid, so it's just a fast peroxide acid-base reaction. So then if you look at this protonated species, okay, I hope you are sensitive enough. You see, hydroxy group protonated become what? Become water, and the water is a good living group. You want to live, okay? So then it just lives. And this is a slow process. Okay, it leaves. Okay, give you what? Give you if water leaves, you're gonna give a carbocation, right? And this carbocation, if you just let this leave, you will see. Oh, if just let this CO bond break, okay, you should have this. Okay, right? Just breaking this one, you immediately can see this. Okay, but this one. This carbocation, okay, is an unusually stable carbocation because this positive charge carbon is next to a lone pair bearing oxygen atom. And we already saw a few times a lone pair bearing atom has a very strong ability to stabilize the positive charge carbon next to it. And same thing here, because of this positive charge carbon next to the lone pair bearing oxygen atom, you can write the other resonance form, which is this one. Okay, this is because of the fact you can write this resonance form, makes this carbocation really stable carbocation. And these two resonance, which one is more important? These two forms, The left side one more important or right side one more important? The left side one because extra bond. Okay? So this is the reason why, hemiacetal to acetal conversion only happens in acidic environment, because in a basic environment, you don't have a pathway for an OH group to leave. Okay, in acidic environment, you have a feasible pathway for the OH group to be protoned and leave. Then you let the reaction to proceed to next step. Okay. So, and then this carbocation, and obviously, carbocation is electrophilic, highly electrophilic, can react with another, the more of alcohol, give you the addition product. Okay. And this product is just a conjugated acid of the acetal. And the last step is the acetal, okay? The loser proton, okay, give you the final product, okay? So I'm not gonna go through the last step. It's pretty straightforward now, okay? So this one is actually, if you look at the 3 steps, do you see something familiar? Alcohol getting protonated, right? That's the first step. And then the protonated alcohol lose the water, become carbocation, okay? And then the carbocation react with nucleophile. Have you seen this reaction before? SN1, this is exactly the same. Just slightly different way. But still SN1. Okay? But if you look at this reaction, okay, look at the mechanism. See, the whole step is, both stages, okay, they are, you see, they are reversible. Okay, so because both stages are reversible, so the reversible in the sense they are equilibrium. Okay, so equilibrium can be controlled by the Shardy principle. So you actually can manipulate the reaction to pick. Okay? So you can either have a carbonyl compound in its carbonyl form or in its ether form. So how do you encourage the reaction to go to ether form, acetal formation? If you continually remove water, okay? Then the carbonyl compound, if you have a mixture of alcohol, okay, so carbonyl compound become ether form or acetal form. And then what if you want the carbonyl form? What do you do if you want the carbonyl form? Yes, add tons of water. Okay. And if you want the reaction, this conversion to be fast, both conversions should happen in acidic environment, because otherwise it will be slow. Okay, because see, that's the one thing to move the equilibrium. But if you want to move the equilibrium, you have to make sure the reaction at the equilibrium, right? So how do you make sure the reaction at the equilibrium? You have to make sure the reaction is fast enough. So how do you make the reaction fast enough? Add a catalyst and make sure the reaction temperature is high enough. So that's what you do here. Okay. So this actually is a very, very interesting, way for us, we can gain the capacity of either place a carbonyl group in its carbonyl form or in its acetal form or the ether form. So what's value of this, the manipulation to us is because if a carbonyl compound in the presence of alcohol, if in its ketone form, okay, or aldehyde form, this carbon is highly electrophilic, can undergo addition reaction with nucleophiles. And if it's ether form, what kind of reaction you can expect? Ether form. Regular ether, what kind of reaction can happen? In chapter 17, regular ether, what kind of reaction can you expect from ethers? Only one reaction in regular ethers. Anyone recall? Only one reaction. Only ethers, regular ethers only react with one reactor, one type of reactor. Regular ethers, I'm not talking about epoxide. Epoxides are different. They have a 3-member ring, they are highly reactive. Regular ethers only react with one type of reagent. That's what you remember?
Is it H2SO4?
H2SO. That's a catalyst. And usually, it does not react much. Only one kind of reagent, one type of reagent can react with regular. Huh? Hydrogen halide. Only thing, because hydrogen halide is a combination of two properties in one molecule. Very acidic and very nucleophilic. The hydrogen halide except hydrochloride, all highly acidic, okay? But they are the halide ion at the same time is highly nucleophilic. So only one hydrogen halide with the combination high acidity and high nucleophilicity can react with regular ethers. For all other things, ethers are not react. Okay? So basically, you see in the two forms. Okay? One is electrophilic, can potentially react with a number of nucleophiles. The other one is dormant, sleeping, not reactive. Okay? So basically, we can. It's basically they give us the ability to convert an electrophilic carbonyl compound to something not reactive, and this becomes a very important way if we want to do the manipulation of a reaction of other part of the carbonyl group, and we worry about the carbonyl group can interfere with the reaction. And this we can, with this method, we can convert the carbonyl group to a form that's not reactive. Okay, and if we need it later, we can bring the carbonyl back again. And this is called protection deprotection. We can talk about later on. Let's have a break for like 7 minutes or so. And we hear the attendance from you.
Oh,
Huh?
If I go to lab today,
Sure.
Yeah, well, can you take? And yo, we should see it pop.
I only have 3 classes. Are you gonna do that biology?
is it online?
It's